let's just quickly go through what we did in the last class. Okay, so the midterm class would be also considered as a class, so that would be the class for the 12th week, and now this is the 13th week. But since midterm is not a lecture, so the lecture number remain 12s. The lecture number is still 12, so this is the 12th lecture that is displayed over here. But actually, it's the 13th week, right? And so we are on our schedule now. So previously we were a week back and 2 weeks back as well, but now we are on schedule, and so we are going to just inshallah complete by having a class 1 week, one class 1 week. Okay, so in the last class we continued with the memory topic, the cache optimization topics, and in that class we discussed about the basic optimizations. When we talk about the basic optimization, we are just concerned with reducing the average access time. Um, so there were two optimizations that we saw in the last class. That was giving read priorities over write. This was about looking for writes in the write buffers, looking for that particular block in the write buffer, and if that there is no conflict, then let the read miss continue. Previously, the read miss wouldn't continue until you are going to empty the write buffer, but this optimization says that you don't have to wait for the write buffers to be emptied every time when there is a read. Just look for that conflicting block. If that is that case, then only you have to wait at that point of time. Otherwise, you can continue. Avoiding address translation when indexing the cache. This was an optimization where we talked about virtual addresses, and we said that the CPU is generating virtual addresses. So how is the cache going to interpret that? Are we going to include a TLB before that goes to the cache, or are we going to let the cache work on virtual addresses? So we said that okay, both of these have some problems. So the best way would be that you can give that virtual address to the cache, but cache is only going to take that part which is common in both the virtual address and the physical address. So the cache is going to be physically tagged. That is, the portion that is storing is actually the tag of physical address. And by that time, it's going to go and find that tag portion. The TLB in parallel is going to convert the virtual page number into a physical page number. So this is going to save time. You don't have to have the translations before going to the cache. They both are going to do. They both are going to perform in parallel. Then we looked at the advanced optimizations, and there are 10 advanced optimizations. We call them advanced because we are talking about the power consumption and the bandwidth also, along with reducing the average access time. So the first optimization that we saw was to have a small and simple first level cache. The size should be small, and the mapping should be simple, that is direct map cache. So the first level should be small and simple. This is obviously going to benefit the power. The wave prediction was also about saving time, and wave prediction was for two-way set associated or four-way set associated cache, where you're going to select one line of the cache as your prime candidate, and you're going to just only check that particular tag. Checking one line is easier than checking many lines in parallel, even in parallel, because you are going to save the time for presetting the multiplexer. Because if that's the only line, then you can obviously give the value of the word feed directly to the multiplexer at that particular time. So this saves a little time, and this is enough for a processor. If you are talking in terms of nanoseconds, then that's also enough. Right. So third optimization was to pipeline the cache accesses. So not the caches are not going to work in just one cycle. Rather, they are going to do their access in multiple cycles. This is going to be easy for the cache operation, the complicated cache operation, to be divided into different steps as well. And likewise, the cycle times can also be reduced. The fourth optimization was increasing cache bandwidth by multiple banks. This was an optimization where we saw that caches should also be arranged in terms of banks. So even if you are talking about a single level of cache, that cache is not implemented as a single chip. Rather, you're going to have banks there. So bank means that each bank can independently get an address or look for an address and do its work. And if a particular bank is waiting for a miss, then the other banks are still they can still work. And this was our fifth optimization, to have non-blocking caches. That is, if you have one miss, then the other cache, the whole cache should not stop. It should be operational. So we looked at non-blocking caches, which is the same idea, that implement your cache in such a way that a single miss is not going to prevent the cache to completely stall and do nothing. So it can do different other options, different other data accesses, even with pending misses. The sixth optimization was regarding uh, uh, early restart and critical words first. And this optimization was when the word is going to be transferred from the main memory to the cache. Actually, the block whole block is transferred, and the block transfer time is quite large time, because there are many words in that particular block which needs to be transferred. So the critical word first means that the one whose address is provided by the CPU is actually your critical word, and this is the word which is needed by CPU. Now it depends on that particular word and its location within that particular block. So the normal thing is that the whole block is moved into the cache, and then that particular word is gone is given to the CPU. Now this optimization is going to save that penalty, the miss penalty, by providing that word first to the CPU, right? So there are two optimizations here. Critical word first means you do that particular, you fetch that word first from that block, and then do the remaining fetches into the cache. And if that word is actually part of middle of the block, then you are going to continue with the remaining fetches from top of that block later. So that's called a wrapped fetch. And then in early restart, what happens is we load the block in order. That is the order of the block. But whenever that word comes, then it's given to the CPU, and then the remaining words are loaded into the to the cache. So these are different. These were different optimization that we saw in the last class, that was before the midterm. Now, seventh optimization is merging write buffer to reduce miss penalty. So we have already talked about write buffers. So whenever CPU is going to write something to cache, in a write through cache, what happens is that you need to update both the cache and the memory, right? So what the CPU does is it doesn't update the memory at that time, but it writes to the write buffer, and the write buffer is then responsible to write the same thing in the memory whenever the memory is free. Now, from the CPU's perspective, the CPU has done its task, and the CPU thinks that it has written that same word in the memory. That's about the write buffer. Now, this optimization is to merge write buffer entries. Now, what actually is this optimization? It says that if you have got a write buffer, then there are different entries within that write buffer. So I'm going to explain that on through a diagram here. So let's say we have a write buffer which has got say 4 entries. So along whenever there is a write buffer, it has got 2 fields. One field is the address field, the other is the data field, right? And this address field is about where in the main memory do you want to store this word, and what actually is this word, right? What actually is the word. Okay, so now write buffer and have limited entries, so you cannot have infinite entries in the write buffer, but the data field here can be different. So for example, we have different data elements that we can write. We can write a single byte. We can write 2 bytes as well. We can write 4 bytes as well, or we can write, if you're talking about double precision number, then it's going to take 8 bytes, right? 64 bits. So we can have double precision as well. So there are different lengths for different types of words. Now let's say we have a write buffer which has got different entries here, and each entry can hold up to 4 64 bits words, right? And then there is an address over here. Similarly, if each entry can hold this, then there can be a field here which describes whether you want that address to be loaded into that particular. For example, if it can, if this the whole size is 464 bits words, so maybe I'm not interested in loading all of those words. So there can be a valid bit along with every entry, which is going to tell me whether this particular data element has to be written or not. So if I just need to write a single word, that is also an option with me. If I need to write two of them, that can be possible as well. Now, what happens in a merging write buffer, which is the technique which is used in different say the latest processors as well, like i7. What happens is that we try to merge these entries together if we feel that the right addresses is something that can be merged together. So you can see over here in this diagram, the top diagram over here. So what's shown over here is a 4-entry write buffer feed. And let's suppose we are just writing a single 64-bit element. So the processor gives a single 4-bit element to be written at 100 location number 100. So it's going to occupy one field, one address line over here, and then the second time the processor gives another write to address number 108, and it writes some more data to that, right? So that second data is going to be occupied in the second entry. Then later on the processor gives another address that is again a 64-bit number, and that is going to occupy the third entry, and the fourth time processor gives another address along with the data, and that occupies the fourth entry, and now your write buffer is full. Now, if the processor wants to write any fifth element to cache and also to the write buffer, the processor would need to first of all wait for this write buffer to be emptied because there is no more space left over here. Now, this merging write buffer technique says that if your write buffer have data elements to addresses which are contiguous in locations, you can merge them together into a one big entry, provided that your field is sufficient for that. So as we have mentioned in our example, that our write buffer can hold up to 4 64-bit words, but we are not merging them. So if we are not merging them, then every write is going to be occupied in a different field of the write buffer. But this optimization says that you have to check in the write buffer, and if your references are such that they can be combined together, then instead of writing them at different points, what you can do is make them as one big field so that they occupy also a single field in the write buffer, and secondly, they do their operation as a single operation, right? So what you can see over here is what happened is, since the location was 100, 108, 116, and 24, so these are all contiguous locations of 64-bit words, right? So what happens is that we have just written a single address 100 and merged all these data elements one after another, so that whenever this is written, then all of that would be written. And for that, we also have set all the valid bits as 1 because all of them have to be written. So this is an optimization which is going to reduce the miss penalty. Why miss penalty? Because as we have mentioned, that if the processor is going to write to the write buffer, and if the write buffer gets full, then processor has to wait. This means that write misses will have to wait, so the miss penalty is going to increase, right? So instead of letting the processor wait for something, because of merging these entries, what will happen is that there would be different entries in the write buffer still empty, so that the processor does not have to wait on a write miss, and then this is obviously going to reduce the miss penalty whenever there is a write miss. Okay, so this entry, this is optimization, a simple optimization. It just says that you can merge the entries of the write buffer elements together. If they are two contiguous location, you can make them one big location, and then you can write them as a single operation as well, right? Okay, so it would not be applied to IO addresses because in IO addresses, these location might not be to the same IO device. So it could be the case that 100 is a different IO device and 108 is a different IO device. And whenever there is a different IO device, it needs its own address. So because in a merging write buffer, we are just providing a single address and writing the whole thing down at contiguous locations. This cannot be done to for the IO devices, because all these IO devices, if they are two different elements, then they need their own address to start their operation. So in that case, what happens is these processors have another bit to tell them whether that particular field could be merged or it has to be taken as separate. So for example, if 100 is an IO address, is an address of an IO device, then what could happen is, if with that write buffer, it could be said that this field should not be merged. So if it's not merged, then it will remain separate. The other fields could be merged, so they can be merged together, right? So this is simple. G.
So how could we distinguish between IO registers and non-IO registers?
Yeah, that depends on the instructions that you are giving to the in the program. So normally in a processor,
or we go for the combinations, or we go for the combination. If there is a even combination, then it is not non-IO device.
No, it's not about the combination. It's about the instruction. There are two different ways in which we treat the IO device. So we can have a memory mapped IO or isolated IO. So if you're talking about a memory mapped IO, then these IO devices are treated as memory locations. And if you're talking about an isolated IO, then they have separate instructions to deal with. So if you're treating them as isolated IO, then it's easy because they have different instructions. So IO devices have different instructions. So whenever that instruction is decoded, then obviously that particular address would mean that it's for the IO device, not for the memory, right? So okay, so let's move on. So our eighth optimization is compiler optimizations to reduce miss rate. Now this optimization says that in order to reduce the access time and the power and increase the bandwidth, what you can do is optimize the compiler. Now this is the easiest optimization for the hardware person, because they don't have to do anything. It's all about the compiler, right? So they are putting everything to the software and saying that the software should be optimized to do these things. And this is again one of the optimizations, that if you want to improve the performance of the cache, then the compiler needs to be optimized. So if the compiler is optimized, obviously it's going to reduce the miss rate, because if your program is optimized, then because programs can behave in different ways, so there are different techniques to write the same program. So this optimization is all about changes in the compilers to reduce the miss rate. And we are going to talk about the loop interchange and loop fusion and blocking and tiling to make changes in the program to reduce the cache miss rate. Okay, so let's come to loop interchange first. Now let's take an example of an array. Now, whenever there is an array in a high-level language, it's obviously a two-dimensional data structure. But when you're talking about a memory, that's a single-dimension structure. You have a single address for a single element, right? You don't have to interpret two different addresses together to give one element. You have a single address with a single element, which means it's a one-dimensional kind of structure, right? So if you want to store this thing, because this is a two-dimensional array. So a two-dimensional array means that you have got different elements separated in rows and columns. So for example, let's call them with their names: A00, A01, A02, and so on. And similarly for the next, so these are rows, right? And similarly for the next row, you are going to have A10, A11, A12, and so on, right? So, and these are columns, so you can have many columns, but every column is going to have uh, a distinct name over here, right? So we have a matrix, and that's the array which is represented over here, a two-dimensional array. But if you want to store them, then since the memory is one dimensional, you have to store them in a particular order, right? And it depends on the high level language which is going to convert that into that particular one dimensional order. So if you're talking about C or the different other versions, they are going to store this array as a row major order. Now, if you come back to the diagram that we have shown over here, row major order means that the rows are going to be traversed first, and when the row finishes, then you're going to move to the next row, and to the next row, and to the next row. And this is how you're going to store that. So, for example, if I want to store this thing in the row major order, the first element I have to store is A00, right? So, if this is my memory, then the first element would be A00, the next element would be A01, because that's the next one, right? The next would be A02. So that's the row major order, right? Where you are going to start by storing it in this direction. And when the row finishes, so for example, when you are finished with that particular row, then the next element is going to be A10, right? So this is how this is stored in this particular row major order. Okay. So as you can see over here, if C is going, if you're going to store it using C, then in an array pjk, the value of j is not changing and k is changing. That is, we are storing 0, 1, 0, 2, 0, 3, 0, 4, and so on. Right. So j is referring to the row, and k is referring to the columns within that row. So you're going to store all the elements of a particular rows column. Right. And if you want to store that, oh, there's some problem with this diagram here. Okay, just give me a minute. I'm going to just see what the problem is. Okay, so if you're going to store that in a row major order, then that's how you do it. But if you want to store it in another way, like Fortran, then you can do it in column major order. Now, what happens in a column major order? We go from columns to another column, right? For example, we are going to start from this. So first element is still going to be A00. Then we are going to store A10 and A20 and so on, till we reach the last element of that column, and then we go on to the next element. So just I'm going to just correct this thing here. That we have this. Yeah.
Sir, shouldn't it go into 9 into 9 matrix maximum?
What?
A 9 into 9 matrix.
9 into 9 matrix? Why 9 into 9 matrix?
Because sir, 0 to 9 is the maximum limit of one array.
No, it's not necessarily 9. We can have anything. It's not necessary that you have 9. Okay, it's going to take some time. Maybe when I change that, when I had changed the dimension of these slides, there was a problem in scaling it up. So, okay, I'm going to just leave it as it is. We can just understand that with that as well. So I'm going to come back to that. So what happened was this small rectangle that you're seeing over here is actually, it had to cover the whole thing. Okay, the same thing is what I have shown, that if you're going to do that in a column major order, which would be the case for Fortran language, it's going to store in such a way that you have all the elements of a column first, and then you are going to store the next column, right? So in our diagram here, what we said was in our diagram here, what this is going to be something like, I'm going to draw it over here. It's going to be something like A00, then A01, A10, and then A20, and so on, right? And when the whole column finishes, then you're going to go to that this next element A01, right? So this is simple. So we can have both these options with us, the row major order and the column major order, right? So now let's say we have a program which has got two loops, and what we need to is to multiply every element of that particular array that we just saw by 2, and we have written that in two different ways. Okay, so we have written that in two different ways. So in one of these examples, I'll call that the right example, the left one, the left example, the left hand example is going to change the value of j's frequently and k's not so frequently. So if you are talking about getting an element of k over here, and let's say we are storing it in row major order, that is we are going to implement it through C. So actually the elements are going to be stored in this way, right? But the program is taking this kind of um, these statements to go through multiplication of every element. Then in your the right hand side program, what is happening is we are changing the values of k's frequently. That is, we are going to take the first element over here, then this one, and so on, and then we are going to change our j value, and it's going to come back to j is equals to 0, and then it's going to continue and so on like that, right? uh, Sorry, in this way, in this one j is changing frequently, so you're going to talk about k is not changing, k is equals to 0, so you're talking about this first element over here, j0 p00 would be this one, right? Then we are going to change the value of j, which means that we are going to jump over here, then we are going to go over here, then we are going to go over here, and so on. And this second implementation is changing the value of k's frequently. That is going to go for all elements of j first, and then all elements of j is equals to 1, then all elements of j is equals to 2, and so on, right? Okay, so my question is, if let's suppose we don't have a cache with us, right? So this is important here. So we have these two implementations, but we don't have any cache, which it's only a main memory that we have. Which of these two implementation would be better? So if we don't have a cache, which of these two implementation would be better? Show it again. The one on the left hand side or the one on the right hand side? Yes. So both are doing the same thing. If you want to calculate the number of operations, they are doing the same number of operations as well. Uh, because this is an m into n element array, so they are going through all the elements. That's not a problem. The only thing is the statement is jk, the order in which it's stored this way. So if we don't have a cache with us, which of these two implementation would be better? Yes, anyone? Come on, I need an answer. You can write it on the chat as well. Come on, quickly, please. I need an answer. Which of these two implementation do you think, or do you think that both are equal?
Sir, I think so. Both are equal.
Is anyone else?
Sir, can you describe M and M? It is the last digit, yeah, or the maximum value?
Okay, M and N. So we have talked about that here. And yeah, so I said that J, if this is your J and this is your K, right? So J is going till M, sorry, K is going till M, and J is going till N, right? So this is a matrix where N and M can have different values. So J is going till N, so this means there are going to be N number of rows, and K is going till M. This means there are going to be M number of rows, M number of columns, right? So this is what the matrix states over here. So it's J is going till N and K is going till M. Okay, so you can have any value for N or M, not necessary that it has to be um, the same value. You can have it's not necessary you have a square matrix. Okay, so Hail said the other says they are going to be equal. Why are they going to be equal?
Sir, because the matrix will be same in both cases.
Yeah, but the matrix is same in both cases. So but we are interpreting in a different way. So don't you think that changing the loop is going to affect that? Yes. Okay, so let's just talk about what's happening in this implementation that we have on our left hand
So,
side.
so in case if the values are different, then it may vary.
Yeah. So what my question is that we don't have. I mean, we don't have a cache with us right now. I'm going to come to the cache later. We don't have a cache with us right now. So the difference in these two implementation is, so we have you have got the same instruction, both of them. That's not the change. Change is in the order of these two loops. So here what we are doing is we are changing the values of J frequently because that's the inner loop. But in that case, in this case here, we are changing the values of K's frequently because that's the inner loop over here. So the way we have stored these elements is that all the elements having same values of J with different values of K are closer to each other, and then the J changes. So do you think that both these programs are going to perform equally if you don't have if you don't have cache with you? So I'll say that it says equal. Why is it equal? Yes. Do you want to comment, Saeed Haider? I can't hear you.
Hello,
Yeah, now I can hear you.
sir. The count of operations or instruction will
Yeah,
be there in both.
yeah, the number of operations are same. So don't you think there would be any effect over here regarding the way in which you are going to write the program?
I don't know. Maybe
Okay, okay.
the last
So
one will be the
yeah, but
best.
Iqbal Aziz, you also said that they would be equal. Why? Iqbal Aziz.
Sir, because for each iteration we are going to both of the location.
For each operation, we are going to.
We are going to access the memory for each location like J and K. For both of the loops, if we perform the operation for, so we will perform equally.
Okay, that's right. If you're talking about having these two elements, so it doesn't matter if you write the loop in this order or in this order. So both of them are going to perform in the same way. Now this is if you don't have cache with you, right? This is if you don't have cache with you. Now let's talk about introducing cache in our design. So if we have now a cache with us, which of these two implementation do you think is going to be better than the other? or do you still think that they are going to be the same? Now let's say we have a cache with us. Is that going to change anything over here?
Excuse me, sir.
G?
सर आपने ये सेकंड लूप का ये पिक्टोरियल डायग्राम शो किया है, जैसे j is 0 and k is constantly changing, बट ये
Uh-huh.
हमारे पास फर्स्ट लूप का किस तरह का डायग्राम बनेगा? बिकॉज मैंने लेट थोड़ा ज्वाइन किया कि यहाँ पर इटरेशन कैसे होगा.
This is for both of these loops. This is for both of these implements. This is the same thing for both of them, right? This is how it has been stored in the memory. This is how it has been stored in the memory, but this is how you have written your program. Okay, so there is the memory is storing these elements like these in on consecutive locations, but this is how you want to access them, and this is how you want to access them in this case. So which of these two implementation is going to be better?
Sir, the right one. Thanks, sir.
This one here.
Yes, sir.
Why?
Because as the memory represented कि जैसे हमारे पास kth loop है, we will take the whole block of the k, kth 0, kth 1, kth 2, and we will access the location at one place. Yeah.
Okay. Yeah, that's good. When you're talking about memory elements, when you were talking about only having a random access memory with you, that was a different thing, because in a random access memory, it doesn't matter whether you fetch this element and next time this element and next time this element. This is the same as if you fetch this element and this element and this element. So you take the same time in fetching every element, so it doesn't matter as long as both programs are fetching the fetching equal number of elements, then they both are going to take the same time. But once you are going to introduce a cache in the design, then the cache have a different behavior. What happens in a cache is that if you want a word, you don't give a word to the cache. You pick a whole block and transfer that block to the cache from main memory. So if you're going to store the elements in this order in main memory, what happens is that if you are going to fetch the first element, right? So it's going to bring some more elements into the cache. Okay. Now let's see what's happening in our first in the first design, in the first algorithm here. So in the first program, what we see here is the value of j is changing frequently. That is, we are talking about the first element. This would be our first element that is fetched, and along with this, a whole block is going to come in the cache. In the cache, what's going to be the second element? So we are going to change the value of j from 0 to 1. So you are talking about P10 because k is not changing, so it's talking about P10, which means this element. So this element, along with some more elements, are going to come into the cache now. So this would be our second axis, right? Then you're going to change the value of j again, and this would mean that you're going to access this element, third element. Along with that, some more elements are going to come into the cache. Now let's say what happens is that your cache gets full, and so what happens is that you have to replace this block from the cache to make space for more blocks in that array elements. Now when you want to when you finish that inner loop, you're going to change the value of k. So now k becomes 1, right? So when k becomes 1, you start again from j is equals to 0. So you are basically talking about this second element here, but it has been replaced from the cache because there was no more space to have it. So what happened was you have to bring that thing again back into the cache. I mean, you're going to bring that back into the cache. The whole block comes in again into the cache. But what's happening is you're just fetching one word from that block, and you are ignoring the other elements of that block when it's in the cache. This is not going to be good for the access time because you're not utilizing the cache efficiently. Now let's look at this version here. what happens is you are having a value of j0, then you are having a value of k as 0 initially, and then you're going to change the value. That is the first element that you are referring to is p00. That's okay. And along with that, some more blocks are going to come into the cache. Now the second reference, what would be the second reference? You're changing the value of k, which means the second reference is to k is equals to 1, which is already now in the cache, right? So this would be a hit. Your third reference, k is equal to 3, k is equal to 2, is also in the cache. That is also going to be a hit. So only you're going to have one miss and the remaining hits. But in this case, what was happening is you are continuously having misses because you bring in the block, but you are not using the elements of that block, and you are ignoring the other parts of that block. But here, this is always obviously going to give us good cache behavior because we are fetching those. We are using all those elements which are in the cache first before they are replaced, and when they are replaced, you don't really need them again. So this is an example of loop interchange. This is an example showing that simple loop interchange affects the average access time a lot. So in this case, if you have a cache with you, then this program is going to be faster than this program, right? Even though they both are doing the same thing, the same number of operations, but the way in which this is doing is it's fetching the elements keeping in mind the special locality. So if you want to exploit the special locality, the second version is exploiting it because it's going to fetch the one element that you need, and along with it the other elements which are localized and they are probably needed, and you are actually using them in your next accesses, and those next accesses would obviously be hits because you have already brought in that block. So is this clear? Is this clear to all of you? That this one will obviously going to have good cache behavior because it's showing more spatial locality. Okay.
Sir, kindly repeat again. Unable to get your point.
The point is that the difference in these two programs is that you are interchanging the loop. So they are having different inner and outer loops, right? But the way in which you are going to store the elements, the way you are storing the elements is favoring a row major order. So if you are going to access them also in a row major order, this would mean that if you are going to access one element, because of spatial locality, the whole block comes into the cache. So the next elements are also already in the block. So if you have stored them in a row major order and you're accessing in a row major order, this is going to have a good cache behavior. Now, this was not an issue when we had main memory only, because main memory is a random access memory. You can access any location which is going to give you the same time. So it doesn't matter if you access locations which are contiguous or at random. It's going to give you the same time. But when you're talking about caches, then caches exploit spatial locality. So if the block brings in more words which are going to be referred next, then you are going to get benefit from it because they are already in the cache and those elements are going to be hit. So in this second version, what's happening in this right-hand version is that we are accessing all those elements from the block first which has come into the cache. And once they are accessed, we don't access them again. So if you remove this from the cache because you don't have space later on, then you are not going to bring them again in the cache because all those elements have been utilized. So this is going to give you a good cache behavior because of spatial locality, and because you are bringing in all the elements from the block, you are utilizing all the elements of that block, and then you are going to remove that, right? Is this okay?
Yes, sir.
Any questions here? So we are going to take a break now, a small break for 10 minutes, and then I'm going to come at 7 o'clock. So let's take a small break, and then you can join at 7 o'clock.
Sir,
So
does this mean that
okay, I'll take the question at 7 o'clock. So let's take a short break, and then I'm
Okay,
going to take the questions. I'm going to continue from here. Right?
okay, sir.